Hi, this is Dr. Shoikat Majumdar. In this lecture, we will discuss the different aspects of photoelectric effect. Already in the previous lecture, we have discussed what is photoelectric effect, what is threshold frequency, what is stopping potential. In continuation, we will do this lecture. This is under the Unit 5 of Modern Physics course, and the topic is photoelectric effect. Learning objective is effect of intensity and frequency of a light wave on the photoelectrons and quantitative study of the equations, work function and threshold frequency. Already we have discussed photoelectric effect, just recapitulating the previous one. The emission of emission of electrons from a metal plate when illuminated by light or any other radiation of any wavelength or frequency is called photoelectric effect, and the frequency must be suitable frequency. The emitted electrons are called photoelectrons. Here in this figure, we have used the reverse bias. That means this collecting plate is negatively charged. So this one will oppose the emitted photoelectrons. So for a particular, if we increase the reverse more, if we increase the negativity of the collecting plate more, then for a particular potential, no electron will be liberated from this metal plate. This particular potential is known as stopping potential. Now, experimental findings of the photoelectric effect. Number 1, there is no time lag between the arrival of light at the metal surface and the emission of photoelectrons. Number 2, when the voltage is increased to a certain value, say V0, the photocurrent reduces to 0, that is stopping potential. This is always in reverse bias, already I have discussed in the previous slide. Increase in intensity increase the number of photoelectrons, but the electron energy remains the same. So this is the stopping potential. Intensity increase means increase in number of photoelectrons, but energy remains same. Increase in frequency of light increases energy of the electrons. At frequencies below a certain critical frequency, no electron is emitted. This particular frequency is known as threshold frequency. So, for different frequencies, different voltages are required. So suppose V1 voltage is required for the frequency of light nu1, V2 voltage is required for the frequency of nu2, and V3 voltage is required for the frequency of nu3. So to stop the emission of photoelectrons for light falling with the frequency of nu1, the stopping potential will be V1. For light having frequency nu2 falling on the metal surface, its stopping potential will be V2. And for light, when its frequency is nu3 falling on the metal surface, for this light the stopping potential will be V3. So if nu3 is greater than nu2 is greater than nu1, then V3 V3 will be greater than V2, greater than V1. That means more energy is required for light having higher frequency to stop the emission of the electron. Laws of photoelectric emission. The number of electrons emitted per second, that is photocurrent, is proportional to the intensity of incident light. If the frequency of incident radiation is below threshold frequency, no photoelectric emission will take place. The maximum velocity or maximum kinetic energy of photoelectrons depends on the frequency of radiation, not on intensity. Kinetic energy increases with the increase in frequency. That means kinetic energy increases with the increase in frequency. Explanation of photoelectric effect by Einstein, or Einstein's photoelectric explanation. The energy of an incident photon is utilized in two ways. Number one, part of energy is used to free electron from the atom, known as photoelectric work function, and denoted by W naught. Number two, other part, that means excess of the incident energy, other part is used in providing kinetic energy to the emitted electron, that is equal to half mv square. So h nu is the incident energy. First part is used to be the electrons just on the metal surface, that is the work function, and rest of the energy is used to supply the kinetic energy, that is half mv square. This is the photoelectric equation as proposed by Einstein. So h nu is equal to W naught plus half mv square. This is the famous equation known as Einstein's photoelectric equation. Here half mv square, V will be maximum. So h nu is equal to W naught plus half mv square max. So we can write h nu is equal to W naught plus kinetic energy max. So h nu is equal to h nu naught, minimum frequency of light required so that the electrons just on the metal surface. So this is W naught, we are representing it as h nu naught plus kinetic energy max. So maximum kinetic energy is equal to h nu minus nu naught. If nu is less than nu naught, that means frequency of incident light is less than the threshold frequency of the metal surface, no photoelectric effect will occur. That means, so in that case kinetic energy will be 0. So h nu is equal to h nu naught. So work function will be h nu naught is equal to hc by lambda naught. So lambda naught is equal to hc by W naught, or hc means, if we put this one is h means 6.624 10 to the minus 34 into c means 3 into 10 to the power 8 meter per second, and first one is h, its unit is in joule second. So in electron volt we can write it as 12,400 by W angstrom, that means W is in electron volt. So 12,400 by W naught angstrom. If V naught is the stopping potential, then kinetic energy maximum is equal to H nu minus nu naught. So you can write this when there is no liberation of electron, that is the stopping potential is V naught, its energy is E V naught is equal to H nu minus H nu naught. So V naught is equal to H nu by small e minus H nu naught by small e. It is in form of y is equal to mx plus c. That means this equation gives us a straight line. The graph with V naught on y-axis and nu on x-axis will be a straight line with slope h by e. So from this graph we can calculate the Planck's constant, knowing the charge of the electron is 1.6 10 to the power minus 19 coulomb. The number of photoelectrons depends upon the nature of material, the frequency of incident radiation, the intensity of incident radiation, potential difference between the electrons. So these are the points we have to remember: nature of the material, frequency of incident radiation, intensity of incident radiation, potential difference between the electrons. This is the factors on which number of photoelectrons depends upon. Failure of wave theory in explaining photoelectric effect. The light is giving its energy to electrons in the atoms of the metal and allowing them to move around, producing the current. However, not all colors of light affect metals in this way. No matter how bright a light wave you have, it will not produce a current in a metal, but even a very dim blue light will result in a current flowing. The problem was that these results can't be explained if light is thought of as a wave. Waves can have any amount of energy you want. Big waves have a lot of energy. Small waves have very little. And if light is a wave, then the brightness of the light affects the amount of energy. The brighter the light, the bigger the wave, the more energy it has. The different colors of light are defined by the amount of energy they have. If all else is equal, blue light has more energy than red light, with yellow light somewhere in between. But this means that if light is a wave, a dim blue light would have the same amount of energy as a very bright red light. Photovoltaic effect, solar cell. The photovoltaic effect is the basic physical process through which A solar cell converts sunlight into electricity. In different way, we can say solar photovoltaic cell is a device which converts sunlight into electricity. In a typical solar cell, a p-n junction is formed between two types of semiconductor, namely p-type and n-type semiconductors. P-type and n-type semiconductors are extrinsic semiconductors. That means there are impurities. In p-type semiconductors, the majority carriers are holes, and n-type semiconductors, the majority carriers are electrons. Here, this is the solar cell. It is a p-n junction diode. Light is falling on the glass lens. So this glass lens will converge the light and make to fall on the p-n junction diode. So we are going to discuss the construction in different slides. When sunlight strikes a photovoltaic cell, the electron-hole pairs are formed. So this is the properties of p-n junction diode. So light is falling, so its energy is increasing, so there is the electron and hole pair, increased number of electron hole pairs. The electric field existing across p-n junction causes the electron hole pairs to separate. As free electrons are generated, they can be collected via an external circuit and flow from the n-type to p-type material. Thus, the current flow takes place. Here, the upper surface, there are metallic stripes or metallic strips. So this is connected with the circuit, and this is the upper one is n-type silicon. Upper surface is connected with two metallic strips. This is connected to the circuit, and lower surface, this is a p-type silicon. There is a metallic substrate base. So the connection is made with the metallic substrate base. So thus the circuit completes. I am going to discuss the working principle in different slide. In p-type semiconductors, this is the working principle. In p-type semiconductors, holes are the majority carriers and electrons are the minority carriers. Already I have discussed how p-type semiconductors is produced. If we dope trivalent aluminium to tetravalent silicon, so there is a deficiency in electron during pair production. So deficiency electron means there is a hole. So hole is the majority carriers in p-type semiconductors and electrons are the minority carriers. P-type semiconductors are created by doping an intrinsic semiconductor with acceptor impurities or doping a n-type semiconductor. A common p-type dopant for silicon is boron, trivalent material. N-type semiconductor have a larger electron concentration than hole concentration. That means if nitrogen is doped to the tetravalent silicon, then one electron will be excess during the pair production. So excess electron will produce. So we can say N-type semiconductors have a larger electron concentration than hole concentration. The phrase N-type comes from negative charge of the electron. In N-type semiconductors, electrons are the majority carriers and holes are the minority carriers. A common dopant for N-type silicon is phosphorus. This is pentavalent. Pentavalent dopant to be used. So this is the sunlight is falling on a solar PV array. This is the solar cell. This is the module on which glass plate is the glass lens is there. So light is converging and made to fall into this array. So this is the solar PV array. This one it looks like this. So the current that is produced, the DC input voltage, this is the inverter. From this one, AC output voltage is sent to main utility breaker panel, from which it is AC utility meter. Then solar power AC to grid, and from this the energy is distributed everywhere. Applications of solar photovoltaic cells. First one is commercial lighting. Photovoltaic powered lighting systems are reliable and low cost alternative. Security, billboard sign, area and outdoor lighting are all viable applications for photovoltaics. Consumer electronics. Solar powered watches, calculators and cameras are all everyday applications for photovoltaic technologies. Telecommunications. It is used in satellites to supply energy to the satellite systems. So it is used for the wide area of the telecommunications. Residential power. A residence located more than a mile from the electric grid can install a photovoltaic system more inexpensively than extending the electric grid. In the remote areas where there is the problem to install conventional electric supply, if we use solar panels, then we can supply the energy to the remote areas. Over 500,000 homes worldwide use PV power as their only source of electricity, and this one is increasing day by day.